This talk is about the classification of electric machines, or, if you will, the family of electric machines. It's a personal view. Although it is generously hosted by JSOL, it does not represent JSOL in any way. I would also like to thank my friend and colleague Jim Hendershot, with whom I have worked for over 30 years, including the co-authoring of the Green Book shown here. Many of Jim's own presentations have been an inspiration for me in preparing this one. The underlying ideas are theoretical, even academic. I've used a number of illustrations, most of them from the Green Book. I have actually tried to avoid using the most up-to-date photographs because the inventors and manufacturers provide sumptuous illustrations of their work on their own websites and even on YouTube, to say nothing of their publications in learned society journals and trade magazines. While we can't attend the great trade shows, now is a good time to study and enjoy some of that material. It's not my place to steal their thunder, but what I will try to do is to show some ways in which the overall family tree makes sense for the present and into the future. Also, I'm at pains to recognize the history of our great human endeavor in electrical engineering, and so I make no apology for showing some examples from the illustrious past. We will try to see the essential features of the main types of machine and try to understand some of the important relationships between certain groups of machines. We will also touch on the profound effects of electronic control in variable speed drives, and equally the effects of high energy permanent magnet materials. In the diagram, the magnets are colored red. Both of these developments have led to great changes, not only in the machines themselves, but also in the ways in which they are applied. We have also seen in recent years tremendous changes in the demands which society is making on the electric machine. Obvious examples are the propagation of wind turbines, and we're seeing the prospect of hybrid or electric vehicles on an enormous scale. In factory automation and domestic appliances, the developments are no less dramatic. A particular concern in this field is the availability and cost of materials. This is not new. However, it is especially interesting and topical to consider this question as it relates to permanent magnet materials. The question can be briefly stated like this: what would we do if permanent magnet materials became too scarce or too expensive? We will see that magnets are used in several important types of electric machine. If we take them away, we will have to use machine types from elsewhere in the diagram. In the important class of AC drives, the ones colored blue, fortunately, there are some viable, proven alternatives: the induction machine, the wound field synchronous machines, and possibly the synchronous reluctance machine. All these machines share the same power electronic controller topology and, to a large degree, a common control methodology. This means that even if we lost all our permanent magnets, we would not need to lose the pulse width modulated transistor inverter or the method of field-oriented control. This is important because of the huge investment in the manufacture and technology of the semiconductor drives themselves. Outside the family of AC drives, there are other viable types of machine which serve important functions today. On the left, for example, we have the commutator machines, DC at the top, and the universal AC machine at the bottom. DC motor shown here has a stationary permanent magnet field But in many important applications it uses ferrite magnets, which are less expensive and not subject to the same availability concerns as the high-energy rare earth magnets. The universal motor at the bottom is common today in mains-fed power tools and some domestic appliances, but it has the same topology as a DC motor with a field winding instead of a set of permanent magnets. For many decades, the wound field DC machine was the mainstay of variable speed drive systems, and it is still used today in rail traction and elsewhere, although it has been widely replaced by AC drives. Here is a photo more than 100 years old showing the manufacture of the rotor of a fairly large DC motor. The power windings are on the rotor, also known as the armature, and this feature is nowadays seen as undesirable because, for one thing, it limits the speed and the diameter, and the rotor is difficult to cool, so it tends to run hot. In passing, we can observe that the process, the craft we see here, is still practiced today in specialist factories, although there has been much development in materials, tooling, processes, and of course also in workwear. The next picture shows another feature of the DC motor, the commutator. This is a small motor with a rotor diameter of about 80 millimeters. And in fact, this rotor could be from a DC permanent magnet motor or from a universal motor. We can see the connections between the enameled magnet wire and the commutator bars either by staking or soldering. We can see significant signs of wear on the commutator, where the brushes have not only been rubbing, causing mechanical wear and noise and friction, but also arcing, causing radio frequency interference and electrochemical erosion of the brushes and the commutator bars. It's easy to point to the disadvantages of the commutator motor, but we should remember its advantages. In small sizes it can be produced cheaply, and its control characteristics are extremely favorable. So much so that the field-oriented control of AC drives goes out of its way to make the AC motor behave more like a DC motor from a control point of view. Let's return to the overall picture. We can see most of the electric machines in common use, together with the two reluctance machines, which are relatively rare but interesting. Classification is more than an academic exercise. It reflects the organization of the electric machine industry and its applications and markets. The diagram is tuned for the modern era, with plenty to guide us into the future. It also reflects the practice of at least the last 40 to 50 years. If we go back before that, the electronically controlled machines on the right would largely disappear, and there would be more classical machines, such as rotary converters, repulsion motors, specialty traction motors, and others which are practically extinct. On the left-hand side, we see the classical machines, which predate the modern era of power electronic control. The classical machines date back to the 19th century, the late 19th century. In Japan, yes, the Meiji era, in Britain the end of the Victorian era, and in America the Gilded Age. Many have become extinct, but these four key ones are still with us today, often with power electronic controllers. When power electronic controllers started to become seriously practical and commercial, let's say since the 1970s, they were applied in the first instance to classical machines, primarily to the DC motor, and then the induction motor and the synchronous motor. But since roughly the mid-1980s, the electronically controlled machines have become widespread boosted greatly by two technical developments. First, the development of the PWM transistor inverter with field-oriented control, particularly applied to the induction motor, and secondly, the development of permanent magnet, high-energy permanent magnet materials. Over the same period, the market for these machines has increased as a result of the pressure to increase efficiency and the expansion in the range of electrically powered tools and appliances, automotive auxiliaries, and traction and others. So while we have had a look at the classical commutator machines, let us take a closer look at the two classical AC machines, the wound field synchronous machine and the induction machine. A natural starting point for this is a power station, and here is an example more than a century old. Of course we have these installations today, but they're usually much bigger. Over 1,000 megawatts is commonplace, whereas in those days 1 megawatt would have been a big one. Even wind turbines are rated upwards of 3 and even 6 megawatts today. But if we look at the rotor, we see a component that hasn't changed a great deal in all of those 100 years, apparently. But the trained eye will see many improvements in materials, processes, tooling, and of course the hidden elements of analysis used in the electrical and mechanical design. This AC synchronous machine rotor carries a DC field winding with exactly the topology shown in the overview. It even has the same number of poles, 4, as we can see by counting the wound projections or salient poles on the rotor. We can also see on the far right the ultimate source of the field current, the rotor of an exciter mounted on the same shaft. Now let's look at the stator. Here is a close-up, but of course this one is definitely not 100 years old. It represents the most modern technology, and it's from WEG in Brazil. You can find it in the Green Book. It's a neat example of the art, very tidy, well filled with copper, compact end windings, all good, and manufactured in very large numbers. For our purposes here, what we need to register is that this AC motor stator is absolutely the foundation stone of the entire family of AC drives, the blue ones in the overview slide. The overview slide shows this stator only as a slotted punching, which doesn't do justice to the huge variety and ingenuity of the different winding layouts, but it does underline the fact that the AC stator is universal for the family of AC drives. It generally comes with a 3-phase winding in sizes above a kilowatt or so in induction motors or in smaller permanent magnet brushless motors. But in larger ratings, we sometimes see 6, 9, or even more phases. In so-called fractional horsepower induction motors, we see many configurations with only 2-phase windings, both supplied from a single-phase source, but with means to introduce a phase shift between the currents. Now, we can keep that stator, and instead of a DC salient pole field winding, let's have a cage type induction motor rotor. Again, although this type of rotor has been made for more than 100 years, this is a modern example of a fabricated rotor with end wings welded to the cage bars and designed for operation with an inverter. The thing to note about this rotor is that there are no connections. It's very rugged, and capable of much higher speeds than a commutator motor armature. Most induction motors of this type use cast aluminium for the cage winding, but for highest performance, especially efficiency, copper is preferred. Let's go back to the overview chart. We have been focusing our attention on these two AC machines, the wound field synchronous machine and the induction machine. Let's register a very important point. The magnetic field in these machines has a definite number of poles, north and south poles, and it rotates at a definite speed determined by the number of poles and the supply frequency. That is the cardinal feature of AC machines. In DC machines, the field is stationary. Let us now remove the rotor from either one of these machines and replace it with a permanent magnet rotor like this one. This is an 8-pole rotor with high energy permanent magnets magnetized in the radial direction and held in place in slots in the laminated rotor, which also has a profiled surface to improve the waveform of the generated EMF. This motor comes from WEG, and again it can be found in the Green Book. It's one of the most efficient variable speed drive motors that it is possible to make. There is a huge variety in the topology of the interior permanent magnet motor, or IPM. This one from MS Tech in Japan has again 8 poles, but with a V-shaped configuration of the magnets. This type of rotor is popular in automotive traction, electric and hybrid vehicles, and sometimes we see intricate arrangements of flux barriers and slits which are designed to tailor the speed-torque characteristic and help control the power factor. It's also common to build rotors with magnets on the rotor surface, as we see here in this Baldor motor, also taken from the Green Book. This is a fairly large machine, and we can see the step skewing, which helps to eliminate so-called cogging torque and to improve the EMF waveform so that the machine runs smoothly. For very high surface speeds, it's common to fit a retaining sleeve which can be made of carbon fiber, Kevlar, or sometimes even a metallic sleeve. This surface magnet motor, or SPM, is here in the chart. The IPM and SPM are closely related, brushless AC synchronous permanent magnet machines. They have different speed-torque characteristics, but they share the same high efficiency. And of course the rotors are completely free from commutators or slip rings and don't run cool, and do run cool. They do run cool. Shaft position sensors are often used, but these don't wear out in the same way that brushes do, and they don't introduce friction, heat, or noise. Tucked in here is another embodiment of the IPM, the so-called spoke motor, in which the magnets are magnetized not radially but circumferentially. This again has its own characteristics, and it has been used in commercial products where lower grade magnet materials can be used. Now a word about the reluctance machines. We need to distinguish two types, the synchronous and the switched. This is a cross-section of a synchronous reluctance motor rotor with 4 poles. It's a true AC machine with a rotating field. It has flux guides which carry most of the flux in the so-called D-axis or direct axis flux path, and these are interspersed with flux barriers which impede the flux in the so-called Q-axis or quadrature axis flux path. The D-axis path is the main flux path in all electric machines, both DC and AC, while the Q-axis path is everywhere orthogonal to it. In reluctance machines, the D-axis path needs to be highly inductive, an easy path for the flux, while the Q-axis path should allow very little flux. An inherent feature of the reluctance machine is that the flux is excited by a component of the stator current. There is no field winding, and not even a cage-type winding or any other kind of winding on the rotor. It's what we call a singly excited machine, because one winding must carry the current for excitation of the flux as well as the torque-producing component of current. A more or less direct consequence of this is to lower the power factor or to increase the volt-ampere requirement in the inverter for a given power level. Over the last 30 years, goodness, it seems like yesterday, tremendous advances have been made in optimizing the geometry of these machines to the extent that they can compete in certain markets that are normally served by induction motors. It's not my place to advertise products, but I do think the work of Professor Vagati in Italy deserves special mention. It's easy to find this in IEEE transactions. Lastly, we must include the switched reluctance machine. This is not an AC machine. It operates with a series of unidirectional DC current pulses, which are synchronized with the passage of the rotor poles past the stator poles, which are usually wound with 3 or 4 phases. This requires a power electronic converter circuit which differs from that of the standard AC inverter. It also requires its own control theory because the principle of field orientation does not apply. Here is the stator of a venerable example made by Limac for the Swedish door opener manufacturer Bisam and designed by the pioneering SRDL company in England. And here is a drawing of a switched reluctance motor rotor. I can remember Professor Lawrenson explaining to the Vice Chancellor of Leeds University over a canteen lunch that because of the extraordinary simplicity of this motor, coupled with its high efficiency and other features, it was going to revolutionize the electric motor industry and would probably displace even the mighty induction motor. That was in about 1975, and I consider myself to be lucky to have been at that table as a research assistant, gathering crumbs of such portentous wisdom. Since that time, the switched reluctance motor has served a great many specialty applications with great distinction. Technically, it's justified the vision of Lawrenson's team, and personally, this is a good point for me to pay tribute to my former supervisor, who passed away a couple of years ago. It's worth mentioning that Lawrenson also pioneered many methods in electromagnetic field analysis, which of course, thanks to JSOL, is the context in which I'm making this video. I think it's fair to say that for many years the reluctance machines have been kept on the sidelines by the superlative performance of PM machines. It was hard luck that super high energy magnets came into the industry at the very time when the switched reluctance motor was becoming recognized. Indeed, looking back to the 1970s, it was unclear what would become the preferred motor technology of the future. Field-oriented control for induction motors was new and untested, and inverters were cumbersome and not as reliable as they are today. Brushless PM motors were mostly running with square wave 120-degree inverters, which seems crude by modern standards of sinusoidal drives. The race had only just begun. The role of reluctance motors could grow in future if magnets become scarce, while we will always have the reliable induction motor and the wound-field synchronous machine. In very large machines, because of the natural laws of scaling, permanent magnets are not necessarily cost-effective and may even be impractical. It's in small motors, servo motors, and small-scale machinery where we would miss the magnets most. However, those motors, the ones that are smaller than a teacup, don't need such a quantity of permanent magnet material, so we should keep that in perspective. Some of them could be served by switched reluctance or synchronous reluctance motors, especially the precision manufactured ones, while in a few cases the good old DC commutator motor might come to the rescue. I don't think we will have to wait too long to find out. Thanks for listening.